And welcome to yet another problem solving session. The problem looks to me quite simple, and the problem is there are two loads with equal masses and they are placed on a smooth horizontal table and attached to the walls by springs with elasticity coefficients. That means spring constants K and 4K. Nice. The loads are simultaneously set in oscillatory motion along the x-axis. I don't see any x-axis, so I'm going to draw one. This could be the x-axis. The first is pushed to the left with what velocity? I don't know. The second one is released, having previously compressed the spring. The spring was initially compressed. How much? But that much, how much compressed, it is not given. But this initial compression must be the amplitude of its motion, block 2. And next statement is the maximum kinetic energies of the loads are equal to E naught. Oh, so I can find how much distance it was compressed, because it's maximum kinetic energy. That means it's maximum potential energy should be equal to E naught also at the initial position, because it has got no velocity at all, so it is simply released. Okay, to what minimum distance will the loads approach each other during the oscillations? If the distance between them with undeformed springs is equal to, this is another problem. It looks simple, but it is not. To what minimum distance will the loads approach each other during oscillation? If the distance between them with the undeformed springs is equal to something, to 2 under root 2 E naught by K. Okay. After what time after the start of oscillations is this minimum distance reached? This is yet another problem, but what can I do? And I can find the amplitudes of oscillation of both the blocks. It was initially at rest and at its equilibrium position. It was given a velocity in this direction, and its maximum kinetic energy is E naught. So what velocity it was given, I know, that is omega A, and its amplitude A1 can be found by simply putting E naught equals half K A1 square, and that gives A1 equals under root twice E naught by K. That's fine thing, one thing to know. And second, how much length it was compressed, A2 length, and this can also be found from the initial the maximum kinetic energy E naught, and that will be equal to half 4K A2 square, and so I can get A2 equals under root E naught by 2K this time. Yeah, E naught by 2K. So, and its angular frequency being omega equals under root K by M, and its frequency omega 2 equals under root 4K by M. That will be twice of under root K by M. That means its angular frequency, if its angular frequency is omega, then its angular frequency is 2 omega. So I got few things. Now we write down the laws of motion of blocks. How? Suppose in the raw form, the law of motion of left block can be written as x equals A1 sine omega t plus phi naught, or like this. So x1 I could write its displacement from equilibrium position as x1. So it can be written like this, and So I can write okay, I wrote this, I can write, not write, and I can differentiate it again. dx1 by dt equals a1 omega cos omega t plus phi naught. Okay, so I need to find out the initial conditions of motion, and at t equals 0 x1 was 0. I take this x1 is x1, we count x1 from here, so x1 was equal to 0 at t equals 0, and dx1 by dt equal to omega a1, yeah, and towards left minus omega a1. So I can put all these things together so that I can get, after putting the values of initial condition in this equation, I can get 0 equals a1 sine phi naught. That means sine phi naught is equal to 0. That's fine. And dx1 by dt was minus omega a1 at t equals 0, and that will be equal to a1 omega cos phi naught. So cos phi naught is equal to minus 1. Cos pi naught is equal to minus 1. So its equation of motion becomes x1 equals what? a1 sine omega t plus phi naught. So I can write here x1 equals a1 sine omega t cos phi naught plus cos omega t sine phi naught, and sine phi naught is equal to 0 and cos phi naught is minus 1. So x1 can be written as minus a1 sine omega t. So I got the equation of motion for left block. Now I'm going to get the equation of motion for right block, and I would start from here, from its equilibrium position, whatever it is, I don't know. x2 equals a2 sine 2 omega t plus something delta naught. Its initial condition may be different, and I can differentiate it, and I can write dx2 by dt equal to a2 twice a2 omega cos 2 omega t plus delta naught, and its initial condition x2 was x-axis was taken in this direction, and its equilibrium position, it was already at x2 equal to a2, initial condition at t equals 0. x2 is equal to a2, yeah, right, at t equals 0, at t equals 0. x2 is equal to a2 at t equals 0, and dx2 by dt is equal to 0. So I can write here a2 equals a2 sine delta naught t equal to 0 I put. That means sine delta naught equal to 1. That is a good condition, and dx2 by dt equal to 0. From here we can get 2a2 omega cos delta naught, and that means cos delta naught is equal to 0. So that I can write it equation as x2 equals a2 sine 2 omega t plus delta naught. Yeah, that's fine, that's looking good. So we can find it, just Expanding the equation, sine 2 omega t cos delta naught plus cos 2 omega t sine delta naught, and a2 and cos delta naught is equal to 0, so this term vanishes, this term, and sine delta naught is 1, so its equation becomes a2 cos 2 omega 2 x2, or but their origins are different, and there were some difference between their origins initially when the spring were undeformed. So instead of writing x2 simply by this, I can take a common x-axis whose origin is here, and I can write both the equations like this. I can write both the equations like this. Look, x1 was simply minus a1 sine omega t, that was correct, and x2, from taking the origin at this place, I can write here x2 equals, what was the initial difference, 2 under root 2 e naught by k, it was plus a2 cos 2 omega t. So these are the equations of motion, and I need to remove them. I don't need them. I was simply writing it. If somebody needs to know how to find the equation of motion, of simple harmonic motion of a block or a body during its motion using initial conditions of motion, you can do in this manner. It is always beneficial to do something like that. So we have the final equations like that. Then the equations of motion of loads, and distance between the blocks is simply delta x, that can be written as x2 minus x1. x2 is ahead, so I wrote this x2 minus x1, and so that x2 minus x1 can be written as, that means delta x can be written as twice 2 e naught by k plus a2 cos 2 omega t plus minus this minus minus plus a1 sine omega t. This is delta x, and when it reaches its minimum value, when cos 2 omega 2t becomes minus 1 and sine omega t becomes minus 1 simultaneously. And I wanted to say that the minimum value of delta x is simply twice 2 e naught by k minus a2 minus a1. And that you can get something like under root e naught by 2k. This is the minimum distance, and it happens at the moment when cos 2 omega t and sine omega t simultaneously becomes equal to minus 1, and this is the time you can get 3 pi by 2 omega plus 2n pi by omega, and where n is 0, 1, 2, 3 integers, and like this. So thank you for watching.